Hi everyone, welcome to the third live event in the Robotic Vision MOOC, and you get to meet the TAs today. My name's Obadiah, and joining me here are James and Ed. So I thought what we'd start is we just go around the table and we'll just talk a little bit about who we are, what we do in the MOOC, and what we do here at QUT. So let's start with you, James.
Behind the scenes stuff, I build the check understanding questions, quizzes, and MATLAB tasks. I'm in my final year of my engineering degree, doing a mechatronics major, and looking to do a PhD with uni here next year.
Thanks, James. And Ed?
Yeah, my name's Ed. I'm a final year PhD student working with Michael Milford and Peter. And I work on things like visual place recognition, which I'll talk about soon. And I'm the one who helps with a lot of your discussion forums, which are questions, which are excellent. And hope to see you all more.
Thanks, Ed. So my name's Obadiah, and I'm also here on the discussion forum, helping you out with some questions. And I'm in an early stage PhD, just started a few months ago, here with Peter Cork as my main supervisor. So before we really get into what we're interested in robotics and in research, I thought we'd start right at the very beginning. What actually got us into science and engineering in the first place? Was it something that we've always wanted to do, or was it a spur of the moment type thing? James?
Well, this is my second degree. I've got a bachelor degree in science, chemistry and maths. I worked a few years in the pharmaceutical industry and realized that I ended up in a job that I didn't particularly like. I decided that I wanted to get into something where I was working towards a final goal and could either just display or get my hands on my final product, I guess, in order to work towards a better goal.
It's really cool to actually have something where you can get your hands on something that you've created from start to finish and own it. Can you, just out of curiosity, can you tell us about what you actually did in your job in the pharmaceutical industry?
I started in QAing, just in the QA and QC area. I moved into R&D in a generic pharmaceuticals lab. Later I moved into QAing and ended up in a lot of documentation stuff, regulatory stuff, and it just got really kind of dull after a while. So decided it was time for a change.
Fair enough. That's cool.
I think I probably got into engineering in a similar way to a lot of people as a young kid, pulling stuff apart, breaking things we probably shouldn't break, seeing a lot of sci-fi movies, robotics. I was at the end of primary school when mechatronics first became a thing. So my dad actually mentioned to me, oh, you should see this. They're actually building robots. It's like in the movies. And here in Australia, we might be a little bit, or we were a little bit behind the curve back then, but we're certainly catching up now. And yeah, basically just worked towards the maths and sciences at school and kept breaking things, kept learning things, soldering, all that fun stuff. And yeah, just went from there.
Yeah, I think we had a question in the last event actually on what's one of the best ways to get into robotics and mechatronics, and I think the best answer is actually just get out there and, well, I think the answer given was to build things, but I guess in your case it was break things.
And then fix them.
And then, that's important, isn't it? For me, I also started out watching science fiction movies. Star Wars, I think, was a really big one, watching all those crazy spaceships and robots and things moving around, and I kind of wanted to see a future where that was kind of possible. And it's pretty crazy if you really think about what's happened in the last decade. And we're in the stage now where if we showed what we have to someone 20 years, 10 years ago, it'd feel like science fiction, but we kind of take so much of it for granted because it's an incremental process of innovation and evolution. So I give the stock standard answer. I went into maths and physics in high school and like that, and then in the back of my head I was always like, I wanted to do spaceships and robots and things. For me, I actually started my undergraduate in avionics. I didn't do it in mechatronics, so that was the spaceships side of things, and then fell into mechatronics and robotics, which I'll talk about in a little bit. So what we'll do is we might just talk about our research or our final year thesis in your case, what you're actually doing. Start with you, James.
Yep. I'm currently investigating the use of multimodal deep neural networks for control of a robot in a simple task, just corridor following at the moment. At the moment, I'm working in a simulated environment, recording laser range data and simulated vision data, using ROS and player and stage. I'm using this data to train in an unsupervised manner restricted Boltzmann machines and deep Boltzmann machines, and currently learning features and hidden representations of this. Eventually, I'll be using both modes, the laser and vision, in order to train multimodal networks, in order to create a rotational and forward velocity for the robot. I'm hoping to have a working system before the end of the year, just in simulation, and we'll then be working on a real world platform, robotic platform. And we're, among the potential applications that they're looking at is to have a self-driving car without the need for explicit programming. So that's one of the main goals, is to try and avoid the need to program every single instance into a system.
That's
Pretty awesome.
Yeah, that's a really cool application, because I think, you know, we hear about self-driving cars at Google and things, and they look really shiny, but the amount of
definitely
hard coding of all the edge cases and obstacles and scenarios that they can come across, the list is incredibly long. Is that something you want to continue doing when you do your
definitely.
PhD?
I'll be looking at continuing this on in my PhD. We're hoping to follow the path of a recent paper done by Google DeepMind, where they used deep learning and reinforcement learning to train a system which became better than an expert Atari player in Atari games. I know another PhD student here is working on some of that stuff in order to get a robot driving around as well. So
yeah, that's a really cool paper. I think we might try and link that in the discussion later on.
Yeah, and we talked about deep learning a little bit on the DF as well, where one of the huge advantages is obviously you can do more generic learning paradigms and then translate those things to unseen environments. So when you say you're not having to train specific instances of things, you mean like poles, intersections, that kind of stuff?
Currently I'm working in a very, very simple world. It's straight and curved corridors, but I'm hoping to see how that translates into more complex environments and what we need to do to sort of train them up in that way. But yeah, it's early progress, early stages.
Awesome. Yeah, as I mentioned, my work is on visual place recognition, which is, it's all about seeing a place and being able to recognize it as either novel, in which case it's new to you, or familiar, meaning you've seen it somewhere before. And this has many applications, like self-driving cars, like James talked about, or corridor robots, or basically any other autonomous system. And so I've been doing this for about 2.5 years under Dr. Michael Milford and Professor Cork. And there are a number of really big challenges. So many, in fact, we have a huge amount of people in our lab working on it. We've got at least a couple of senior academics, a professor, Peter. We've got about 4 PhD students and about half a dozen postdocs. And some of the biggest challenges are what happens when the environment changes? What happens when you see a place again at night? The lighting's different, the lighting might be poor, seasons change, all sorts of things change, like the types of cameras might change, the viewpoints might change. And these are all things we're working towards solving. And in my research in particular, we're trying to do it with a training-free approach. So rather than learning about how environments change, we try to just accumulate enough information, which we do using sequences of images. And I'd just like to show a video of some of the harsh conditions we can recognize for us. We can just flip the screen. Other one. So these are the sorts of environments our algorithms can currently match across, requiring No explicit environmental training. This is just a road-based data set where we've encountered a particular place during the daytime and then revisited it at nighttime. And you can see there's a huge perceptual variation. And I guess one ultimate goal we're working towards is this concept of a vision-based GPS system. So traditional GPS does have some problems. In urban centers, you get a lot of reflection of radio waves, which I think Peter's also talked about in the MOOC. Vision doesn't have these problems, and it will also work in places like tunnels where signals don't propagate through. So I'd like to just close with another video, which is sort of our promotional stunt video for our work. And this is sort of the end product we're working towards.
This is the exciting camera-based GPS system developed by the roboticists at the Queensland University of Technology. It's an innovative system that uses video images to recognise a location and ensure that you never get lost again, even when you drive into a tunnel. This is how it works. Vision of a roadway is stored in the GPS's memory or downloaded from the cloud. The system's software then converts these images into contrast patterns. These contrast patterns change from image to image as you travel along the road, and it's the sequencing of these patterns that this GPS examines. These image sequences are like a fingerprint and are unique to every location. So by looking at the images of the sequence, this GPS can match it up with sequences stored in its memory and will recognize a location. It's a simple system that will work anywhere your camera can record an image. And as you'll see in the following example, it even works well in low light and poor weather conditions. In this test, vision was recorded of a roadway on a sunny day. The system converted the images into contrast patterns, and when the same route was driven on a rainy night, the GPS was able to line up the contrast patterns in a sequence and make a positive location match. Another strength of this GPS camera system is its ability to connect to images uploaded by other navigation systems, as well as to existing online images from road networks. So, when your satellite GPS fails, you can rely on this innovative camera-based system to guide you through the world and deliver you to your destination.
Okay.
All right, sorry about those volume issues we just saw your messages about. We'll post a link to that in the show notes, so you can all go and check it out yourselves if you like. Obi?
All right, thanks, Ed. So my research is kind of, it's a part of a project that was already started when I sort of began working here at QUT. And it's inspired by this idea that robots at the moment, they're really restricted to operating in constrained and previously explored environments. You kind of really only deploy them in places where you already know what's going to be there. And we're sure we've got these great obstacle avoidance and algorithms and so forth, but really we have some idea of what the layout of the place is, and we do some previous mapping of the floor or the room before we actually send the robot out to perform some task. And it's really, we were sort of looking at how humans behave, because we don't need a map of a place to go places. that we've never been before. And actually, if you talk to a lot of people, they'll say, "No, we never look at maps. We never ask for directions." There's that whole train of thought as well. And there's a whole bunch of existing information out in the world already, which includes things like street signs and building names and room numbers that are specifically and explicitly designed for human navigation. And we thought, why not use this sort of spatial navigational information to help robots navigate? So my project fits into that research by actually looking at extracting the information from things like street signs and door labels. And this is done visually from a camera image, and it's based on text recognition. So if you've ever done, I think the very earliest case of it is flatbed scanners, and you scan a black and white print document into it, and they can tell you what text is there. That was sort of the very first instance of the acronym is optical character recognition, OCR, and you can get libraries and code for your computer to actually do that these days. But that really only works in, again, constrained environments. You know, it's going to be a white background and black text, and it's got to be a certain font and a certain size. And if there's shadows or anything, you know, it freaks out and starts giving you gibberish. And I can tell you the gibberish is pretty spectacular. So what I'm looking at is how can we extend this to scene text or text in the wild, where you don't know the environment, you don't know what color the text is, what color the background is, what font it is, how big it is. The text might be vertical or curved. You might get obstructions. It might be behind a tree or something like that. And so the first part of it is actually looking at training a system to be able to recognize text in some unconstrained environments. And what I'm working on at the moment is some really cool work by Oxford, where they actually train a neural network with entirely synthetic data. Because if you think about text, it's a very interesting case where you can actually generate this synthetically, because text in the world is actually originally synthetic. It's been created by some person on some computer, printed out and put up in a sign, or there's some edge cases where it's actually handwritten, but I'm choosing to ignore that for now. And so that's one of the first things I'm doing now, and what I'm actually working on today is trying to generate this synthetic data, and there's about 8 million images that I'm trying to generate, so that's going to take a while, but I'm just going to let it run and see how that goes. And then the second part of it, which because I've only been here for a few months, but I'll probably try and get onto this as my PhD progresses, is to look at, you know, what happens if some text is obscured. You see a street sign and it's behind a tree. You can kind of tell it's a street sign. You can see a couple of characters, but you really can't read the whole thing, even as a human. But we're on a mobile robot. That's the whole point, right? We're trying to move this robot somewhere to get to some goal. So why don't we actually recognize that this text or this information has been obscured, and move our robot around using some active perception and actually get around this obstacle to try and get a better view of the text. And that's really one of the things that I like to try and tackle in the next few months or the next year or so. So that kind of sums up our research. Let me just see if...
Yep, so we've had a number of pretty good questions so far. So Paul writes, the vision system looks really cool. It seems that it might be vulnerable in drastic changes like natural disasters. Yeah, this is a valid concern. Obviously, you can't really account for things you haven't seen. You can't magically generate knowledge. I mean, you can learn to adapt around things. In the case of this system, where we're using sequences of imagery, there is some expected similarity. So I suppose if you had like an asteroid take out the middle of a city, you'd be pretty much stuffed. It wouldn't work. If you had, say, a construction site where a building's missing, you'd probably still get enough information from the sequences of imagery before and after that event. You can compensate by increasing your image sequence length. That does introduce a lag, but you accumulate more information that way. The other thing, which is what we're working on now, is using particle filters and integrating motion information with odometry. So, for example, with a car, your wheel encoders are actually really quite accurate. So if there's a long period where you just can't localize, maybe your camera just stopped working, or a natural disaster like in this example, Generally, you can keep up with odometry and then maybe pick up the localization back at the end, and you won't really lose sight of where you are.
So I think Jack has just arrived. Hopefully he comes in the door very soon. And so when Jack gets here, we'll get him to talk a little bit about his research as well. And in the meantime, we might just start answering some more of your questions that you've posted here. So we have a question about artificial intelligence and whether we think it will emerge in the future or not. I've heard a kind of a line of thought that says that anything that we can come up with that we can teach computers to do, that will never be considered artificial intelligence, because if computers can do it, then we're not really amazed by it anymore. So if you agree with that, then I guess you can kind of argue that maybe artificial intelligence will never be a thing unless you really get computers starting to create their own code, which may happen in the future, but I don't see that. I don't see us being anywhere close to that right now. Do you guys have any opinions on the matter?
I think anyone who's seen real robots knows we're a long way off
Yes.
from anything like that happening. You do go down that beaten path of robot ethics as well, which I think is so far away it doesn't bear thinking about yet. Like, should a robot have a passport or something?
Yeah, no, I completely agree. Like, if you watch what our robots do, you really can't imagine them taking over the world at all when they're running into glass walls and reversing into glass walls when you've taught them not to run into glass walls head first. One other thing with this whole concept of the AI singularity and I guess Armageddon, doomsday type scenarios is that because so much of our world is now automated, that it may not actually look like nuclear war or robots running around our homes and shooting us. It may actually just be something like some fault in the internet causes some issue in the system, and that might knock out power to an entire country, and that would be pretty catastrophic. So just something simple like that, where it's just a bug in the code or someone's made some mistake somewhere and some error has cascaded through the system and hasn't been caught, that could be pretty catastrophic as well. Do you have any opinions, James?
I know recently Elon Musk and Stephen Hawking have both mentioned that they're terrified of potential artificial intelligence, but there's people working in the field like Andrew Ng who have no issues with that at this stage. They're saying it could be well and truly centuries off before we're anywhere near that sort of stage. So
yeah, I think what you have
I'm
to
not worried.
Yeah, agreed. I don't think any of us are really worried. I mean, we could be wrong entirely. But,
Yeah.
We could be wrong. But I think if you really understand what's happening with what is probably the closest to artificial intelligence with these deep learning sort of approaches at the moment, the most, I guess, impressive results at the moment we're getting is from deep learning. It's not really something you could call artificial intelligence, where it's kind of model matching or pattern matching, where you try and fit a curve to some data, and it's just doing it in a very sophisticated, very fancy way and achieving really great results, but it's not really thinking for itself or making any intuitive understanding of the scene or anything.
Yeah. So I think when most people hear the word artificial intelligence, they think of this consciousness, like sentience, maybe something like Terminator. Whereas in practice, the field of artificial intelligence is like a subset of machine learning, where it's basically search algorithms and pattern recognition.
Cool. So thanks for that question. Let's move on to. I'm just trying to bring up this. We've got a question from Cameron Whiting on when did we get into computer science and how QUT fit into that. I think we kind of touched on this at the beginning when we introduced ourselves. For me in particular, I chose to come to QUT just because there was a really attractive scholarship offering, which is called the Dean Scholars Program. And that was something that came up when I was applying for university courses in my final year at high school. And I was kind of thinking, well, if I get into that, then the scholarship paid for, at the time, it paid for all the university tuition. So I thought, why not apply? And since I was applying for that, I just kind of put QUT as the next option. So QUT scholarship, QUT without the scholarship, and then I chose all the other universities below that. I think also there's a bit of what word do I want here? A bit of an atmosphere around QUT of we really encourage real world examples and hands-on practical learning. And I think for engineering, that's really important. That yes, theory is important. Yes, you need to know the fundamentals of mathematics behind why you're doing it. But I think you learn the most when you're actually hands-on and applying it to a project. What about you guys?
Yeah, well, I actually came from a different university, which was University of Queensland, which is a fairly big one in Australia. As for how I found about QUT, they developed, so Peter Cork and another professor named Gordon Wyatt opened up this new big robotics initiative here, which is certainly the biggest in Queensland, and they just had great plans to expand and to get all these new students along. I actually had a lecturer at UQ that made the move over, and he said, come and talk to us, and all of the projects were exciting, so I picked one and basically got on board.
I hadn't decided which stream of engineering when I first joined QT, but I knew it had a good reputation as an engineering school, and so that sort of led me to here. Yeah, that's mainly good.
All right, thanks. So we've got a question here from Paul, who's asking some really good questions. He asks, first of all, what do we plan on doing after we receive our degrees? Are we staying in academia, or are we hoping to work in the industry? Do you want to start out, James?
So yeah, I'm definitely looking at PhD here next year. Beyond that, that's a few years in the works, so I haven't got much plans at this stage beyond that.
So I'm a few years beyond that, and I still don't know. At this point, I'm keeping all doors open. I quite like what I do, but at the same time, a PhD is quite a long project, and in some ways you want to branch out or move somewhere else. And yeah, certainly vision's exciting, and it can lead to many pathways. So I'd be open to either industry or further research.
Yeah, and it's the same with me. I mean, again, I'm still a few years away from finishing my degree, but at this stage, if there's an attractive job in industry somewhere, I would take it. But I couldn't see myself going into something where. So one of the reasons why I left the avionics industry in Australia is because there's really very little innovation happening, at least at the time that I was looking for a job, and it was mostly maintenance and upkeep of the current air fleets in Australia. Australia's not really a hub for aerospace innovation or research. So I couldn't see myself, entering data into a spreadsheet, doing documentation. And I mean absolutely no offense to anyone who does that, but I get really jittery and restless when I do repetitive tasks. So that's just me and my personality. So I couldn't see myself going into industry if it meant something like that, but definitely keeping my mind open. So the second question Paul asks is, what are the hardest problems we've faced while pursuing our degrees? So I kind of want to talk about really briefly this project that we did in avionics, our third year project, and it was an autonomous blimp. And if anyone's ever tried to actually, if you think about what that even means, you understand that it's ridiculously difficult, because control of a blimp to start with, you can't really control it because it drifts, right? You can kind of pulse the motors and it goes forward, but then where it goes from there, you really don't have any control. And autonomy of a system, it's a big undertaking, especially at the stage of our collective human knowledge. So as a third year undergraduate student, that was a massive undertaking. And that was probably one of the biggest challenges. And I think what was ultimately our downfall was we didn't understand electromagnetic interference. So we had this magnetometer, which was part of the inertial measurement unit, the IMU, which was giving us heading and direction and all those kinds of things. And it was being affected by the lights. So it was about 90 degrees out from what the truth was at all times. But it wasn't a consistent 90 degrees. It might have been 90 degrees this way or 90 degrees that way, or it might have been right, and we had no idea. So it's basically just the blimp went wherever it wanted, and we couldn't really do anything about that.
I think either my uni copied this one or yours copied us, because we did a very similar project and it was a nightmare. So those magnetometer things are digital compasses, and they get hugely interfered with by like a table leg, for example. So you'll be smoothly going along and heading north, and suddenly it will think you're heading south or something like that, and the blimp will just drift away or float off into the sky. It's very fun.
And James?
A bit more on different sides, things like time management. I'm not apparently very good at, I've found. I'm coming off the back of 2 very late nights, so I'm a bit out of it at the moment. Undertaking a degree, I think, multiple subjects, multiple projects at one time, so something to definitely try and get a handle on Still working on it.
Thanks. I'm just going to see if Jack's outside of it.
So Hamilton asked a question, what is sequencing? Sorry, I probably didn't explain this well enough. When you talk about place recognition, sometimes you just look at the image classification context, which is you take two images and you say, is image A the same as image B? And if you do that, you're limited to the information solely contained in those two images. What's somewhat unique about my approach is we do that with sequences of images. So instead of saying, is image A the same as image B, we say, is sequence image A the same as sequence image B? And this could be anything from 10 frames of imagery to something like 1 or 200. So the more you use, the more information you get, although it's more complicated with more of them. Jack, welcome.
How you going?
Hey, do you want to give us a bit of a brief overview on what you do just as part of the MOOC team and as at QUT as well in terms of your research and your final year thesis?
For sure. Hey guys, so some of you might know from Introduction to Robotics that I've been working on a gripping hand that is designed to grip capsicum. Now, my thesis is coming to an end, and so basically what I've done is I got a gripper design that's open source from Yale University. Now this gripper design, it can be printed out, which is really advantageous as it allows you to redesign the gripper really quickly, like rapid prototyping. Now, I've made quite a few changes to it because originally this gripper was designed so that it could grip a multiple amount of objects. So it could, pick up a whole bunch of stuff. We only needed it to grip capsicum. So I basically just optimized the length of the fingers. I added knuckles into it because we ran into an issue where when you grip a object, it had passive compliance. So if you look at your hand, your fingers move up and down like this, but they'll only move a fairly small amount. And the fingers in my gripper would actually move far too much in that direction. So I added knuckles in to prevent that movement. So far, I've tested it in the field and it gets a fairly decent grasp. Software-wise, I still need to add in some code because at the moment it just grabs as hard as it can, and that's kind of bad because it nearly breaks itself sometimes. But yeah, that's what I've been working on that way.
Yeah, cool. Do you want to talk to us as well about if you have any plans on after you receive your bachelor degree? Are you thinking academia or industry, or do you not know yet?
I do not know yet, which is bad. But I am going to move into industry. I won't be going into academia when I finish. Hopefully I can get into robotics. Realistically, I'd like to do something that's really technical and in automation. So factories and all the automation processes behind that, that'd be really cool to get into.
That's great.
Yeah.
We have some individual questions just left over from Paul. So the first one is to Ed. And how did you come up with the idea for your sky blackening?
Good question. So that first video I showed earlier with the day-night matching through a CVD environment, when we first ran our existing algorithm on it, there was absolutely no hope in matching that at all. And so we sort of looked at the lighting changes. There's this color inversion problem. You get different reflections off the glass on the buildings. But what stuck out the most, because we do this whole image matching technique, is that the sky has a huge amount of pixels within each image. And those pixels are completely useless for localization. They don't tell you anything, and they'll change when the weather changes. So we thought, what's the easiest way on the whole image level to downweight the sky, and that's simply to make those pixels black. So we did a brief literature review. We looked at sky segmentation techniques, and keeping up with the theme of training free, we found a technique by another university here, the University of Queensland, where they did something very similar for their biologically inspired UAVs. And we sort of borrowed their technique and tweaked it a little bit to suit our requirements. But the closest thing you can do with any sort of daytime sky, be it clouded or overcast, is make it black, and then it matches a nighttime sky really well.
Great, thanks for that, Ed. There's a couple of questions here addressed to me about when my latest paper becomes available, and also about how I actually do the synthetic text generation. So at the moment, I've got a paper and submitted for review for an international conference called IROS, Robotics and Systems, I think. Yeah, I think that's what it stands for. Hopefully that gets accepted. And so that should, I'll probably hear more about that in a few months. Normally what happens, I think, in robotics is the big conference acceptance, the paper submission date is around September, October. You probably know more of this.
Yeah, August to October.
Yeah, he's done this a few times before. This is my first
time.
Yeah. So we're, I'm planning some publications for there as well, but we'll see how that goes. In terms of how I do the synthetic text, there's actually a really interesting paper by Google where they've solved their capture algorithm, and I suspect that's because captures are entirely synthetic, but that's my theory, and I don't know enough about the subject to say authoritatively on whether or not that's the case. But so we use the process that Oxford use, which is to actually try and render the text in a method that is as close to the real world as possible. So you do lighting change across the image, you do some shadow, you do some borders, and this is all random, right? So you randomly generate some shadow. Maybe there's a shadow, maybe there isn't, and some random background, and you blend all these layers, all these image layers together, and you end up with an image that actually looks really astonishingly like what you'd actually get out of a camera. It's all grayscale, but it's still pretty spectacular, and I'm just trying to replicate their code at the moment, and I'm kind of almost there, and it looks pretty good. So yeah, if you're interested, we can talk some more in the comments and so forth. And finally, a specific question to Jack, and how do you do iterative development for your hand design? What challenges have you encountered, and have you any concerns with the 3D printing approach?
That's a good question, because when you're faced with designing a hand, how do you design a good one? How do you know what to do to design a good hand? I approached it two ways. One was empirically, so I would literally print the design out, test it, does it grab, what are the problems, does it slip in this section, or from this angle, does it not get a strong grasp? I also created a simulation in MATLAB, which was fairly decent. The simulation only really confirmed what I got from my empirical testing. So I held it against the capscan, a bunch of different types of capscans, and I came up with an estimate of a length for the fingers, and I think it was like 10 centimeters or something, and then I simulated it in like perfect conditions and optimized it, and I think that came out to being like 10.3 centimeters. So they both came out really similar, doing a simulation test and an empirical test, which is kind of cool. So yeah, basically to come up with a good design, I realistically had to check, so I get the capscan, I'd come in from an angle and I'd go grasp. If it grasped it, I'd go, well, that's a success. And then I'd move it so you have the capscan here, come in from here, success, come in from here, success, come in from here, fail. And then I go, okay, that didn't work. I'll try putting on these different fingers, coming from the top, and then just continually repeat that heaps and heaps of times until eventually you come up with a design that's reasonably good at all directions. The 3D printing part, I haven't run into too many issues. The only ones that I run into are when you have a CAD model and you design something, you go to 3D print it, and then you have all the parts, and then you realize you didn't think of how to put it together. So you just got a bunch of 3D parts that can't go together, and then you have to, like you can't get a screw behind something. You get that. So that's the only bad thing. Other than that, 3D printing's a pretty good way of rapid prototyping.
Great. All right. Thanks for that answer. We're probably just on the edge of our time here. So do I want to invite any closing remarks from anyone? Does anyone have any comments?
We're happy to take any further questions you leave on the forums for us. So.
Yeah, so there's a couple of questions that we haven't managed to get around to, so we'll try and answer them on the forums. And if you have any further comments or questions about what we've talked about, please do come and talk to us. We really do appreciate these questions, and it's great to see so much interest in the stuff that we do, because it's kind of it affirms us, it makes us feel all warm and
awesome.
and fuzzy on the inside, like our lives aren't a waste.
We've got Obi on watch.
So so thanks everyone. We'll put links to all the things we've talked about, the papers and the video as well, again down the bottom. And thanks everyone for watching. Have a great day.
Thank you. Bye.
Thank you.